All right, so let's go ahead and talk through some of the information necessary to complete this next lab. So here we've got rotation and moment of inertia. We're going to look at basically a version of what's called an Atwood machine, where we have two blocks suspended on a string that's run over a pulley. So a lot of times you assume that's the ideal case, whereas here we're going to factor in the pulley itself. But you may have heard of that system before, and it'll be a similar image to what we're going to look at. Here, again, key information and some formulas to begin. So we have a definition for torque. Newton's second law is repeated again, and some information about moment of inertia for the disk for the pulley. Okay, then what we're going to see for average velocity is the same formula we've seen a few times. Because these can only move vertically with the way that they're hanging from these strings, then everything's delta y instead of delta x, but similar format. We want to find the change in position divided by the change in time, which we're going to take based off of our readings from data points. Okay, then we're going to follow up with a percent difference formula, which we have also seen before. Basically, what you want to keep in mind with this is that whatever you expect to be true is the number that's going to be used multiple times. So theoretically accepted value, basically what you expect to be the right answer, is going to be subtracted with your one that you're trying to check, then absolute value of the difference there. So it doesn't matter if it's positive or negative, high or low. We just want to know how much is it different. And then we're going to divide by what the correct value should be. And technically that turns this into a decimal. And then we multiply by 100 and slap a percent sign on it to have that listed out as a percent. Once more, these extra formulas and pieces of information can be found at the bottom of your lab data section. So you can find these in little tags and they make these pop-up windows. All right, so our setup, like I said, just a couple of things hanging across a pulley. You can see that one mass seems to be bigger than the other one. And so when we press play, then it's going to move in a way that I hope you expect. Then it asks you which way these are going to turn. I think it should make sense to you that the heavier one is going to control that outcome. But again, I'm not technically going to give you a hint. Try it. If you get it wrong, then check the hint and see if you can fix it. All right, so I guess this picture kind of spoils it, but that's okay. It should be hopefully what you were already expecting. All right, so we're going to start with some similar calculations that we've seen in pretty much all the labs so far. We want to get a conversion on our frames and a conversion on our distances and pixels from the picture here. So this is probably going to change from student to student. In my example, I had 165 pixels wide. You want to make sure to read in the instructions to the side that this pulley is 14.500 centimeters wide. So you're going to use that in that conversion. So for that conversion, if I want centimeters per pixel, right? So I know 165 pixels is this big number. I want to divide those to have an answer. And it looks like you're dividing in a weird way, but 14.500 centimeters divided by 165 pixels. So this is going to give you a small decimal answer, but that's intended this time. And technically our full units, if we were to write them, would be centimeters per pixel. That's really indicated by the 1 pixel in front, but we can use this to see our conversions a little bit later on. Technically, the conversion for the frame is given to you in the introduction section that we looked at first. But in case you have questions about this, it does indicate 60 frames per second. And so if it's 60 frames for 1 second, then 1 frame is how many seconds that we're trying to work through. It's basically going to take and flip that around. So we end up with 1 divided by 60. And that's where we round out and get that decimal number. Okay, and so with those conversions, we can do the calculations that we need. And we only really need to remember one more formula to find velocity here for our initial set of calculations. So we're almost ready. All right, so from here, we move on to phase 3. Then it's going to have us click on the corner of the block to get a data point. Then we're going to do some calculations off of that. We'll look at a second data point so we can calculate velocity. And then once we do our manual set of calculations, then we will move on to the next phase, and we will track out several of them that are automatically calculated by the software. All right, so here, it's hard to see, but that's actually two little crosses. They're just very close to each other because this thing moves very slowly at the beginning until it accelerates and moves faster. So we would take this information from over here on the side. This is the second data point. Like I said, these are very close, but you would read them one at a time, insert your information, do your conversion. There's no time offset on this one. So whatever number of frames gets multiplied by your seconds per frame. So 6 times 0.0167 seconds. Unfortunately, they kind of staggered these funny. That's going to go here. And then similarly, 10 times 0.0167 seconds goes there. Then for our distance conversions to see what these Y positions are, for the first one, 378 pixels. Then our conversion is 0.0879 centimeters per 1 pixel. Again, pixels are technically units here and they cancel each other, but that's going to multiply and give you your top number. In a similar way, you'd multiply with the 380 to get the bottom number, or whatever your values happen to be. Then final calculation we need to do to get started with this part, our velocity. So the Y velocity is change in Y over change in time. So our change in Y, make sure you're using the centimeters and not the pixels. But we're going to have 33.402 minus 33.226. Excuse me. Divided by our change in time, which is again from that other column, so 0.167 seconds minus 0.100 seconds. Then that should give you your velocity. Depending on your calculator or what you're using, you'll probably want to work out the top part, then the bottom part separately, then divide those to get that velocity. Otherwise, if you're not careful how you type this into your calculating device, you may get strange answers. Okay, so next one, where we're basically doing the bulk data gathering. We click on this a whole bunch of times, and eventually it runs through its path, the whole while it's collecting information in your lab data that you can go check here. And you'll have something like this with potentially slightly randomized numbers. Thankfully, after the first one, you don't have to manually calculate any velocities or conversions anymore. It does that for you. Okay, so then once we have that information, we want to put it into a graph and see what calculations we can do. As before, horizontal is typically always going to be time, and then look at what is going on here. It says velocity, and it makes sense. It would be Y velocity because it's dropping down. So for here, we would select VY. The graph is going to be typically a scatter plot. That way we can graph our individual data points and then eventually run some regression on it. So make sure you click create, show regression, and then save so that you have that information. It's going to ask you what you expect the graph to look like before you can actually set it up. So that way you're making hopefully an educated guess without peeking, but put what you think it might be here. Keep in mind the velocity is going to go faster and faster as it goes because gravity is going to help accelerate this. If you get it wrong, read the hint, try again, and then we look at our line here. We're going to pull some information from this. So the acceleration that we seem to have, our change in velocity over time, is related to this slope. Now, unfortunately, there's a minor typo in the next question. So the information we're looking for is here, and you may not see that reflected in the answer it makes you pick, but we're looking for the thing in front there. So that slope, 41.6, gets recorded. If it had been negative, then we would have swapped the sign to make it positive for magnitude. But because it's accelerating upwards, we tend to call that positive, and these just match each other. Okay, then that's what gravity, or this rather the acceleration seems to be from our gathered data. So now we want to calculate what it should ideally be. So there's torque going across this pulley created by tension in the lines on either side. And then the fact that this is a real pulley means that it has mass and moment of inertia that will change how it turns. So click on Newton's second law and you get kind of a lot of information here. I had to zoom out a bit to make it fit in one slide. Obviously, when you see it, you can zoom in close and see the parts better. You're going to want to pay careful attention to our formulas. So these here are going to end up being multiple choice questions, or some variation of these become multiple choice questions. And then at the very end, we need to calculate acceleration, which comes from the bottom there. So that's hard to read from here, but like I said, you'll be able to zoom in and check on your own version. Okay, so as promised, these are going to go over those same formulas. If you've forgotten them, or you can, go from the link here. I think the question blocks you from clicking the orange button now, but they gave you a second blue link. It's kind of a dark blue, maybe it's black, but you can review that same stuff again. So a few of these to answer, again, pretty much straight from those notes. We saw a moment of inertia for a sphere in the last lab. It's a different for pulley. Also, minor typo, there should be a space in that. But, again, this is something you can look up or you can guess and use the hint to pick correctly. We had 2/5 for a sphere last time. It's not that for a pulley. All right, so when we do our calculation, again, you've got that big formula from the bottom of the slide here. Make sure you work out the top part, get an answer, bottom part, get an answer, and then divide the two. And then that's going to give you your answer that goes here. Now, unfortunately, there is an error with this lab. From the examples I've seen, and I've run through a few of these, I always get 100% error, 100% difference. Really, this should be pretty good. This should be like less than 10%. Like this should be a pretty small number. But for whatever reason, it just doesn't calculate correctly. And every version of this I've had has been 100%. So if you calculate the way you're supposed to and you don't get the right answer and it looks like it's being weird, try 100 on this one because you might have an example where it's miscalculated as well. All right, then that's the last piece. So if you finished everything, once again, you get a congratulations. If you've missed anything, submitted early, or ran out of time, then you'll get whatever percent complete.